Thank you, and thanks to Fernando for inviting me here. This is my, in fact, first visit actually to this side of Princeton. I did arrive last night, but only sort of had a few hours to look around. Seems so nice. I'm looking forward to the 3 months. So when Lucas told me to give this lecture, he kind of told me it's meant to be sort of informal. I should use the blackboard, and so on the plane last night I was preparing notes, and he said I have 2 hours, so I was, it's good. That's good. That's fine. I can talk about some proofs and so on. And then I did get to about 11 pages, then, but no proofs yet. And then I realized, oh, it's only 2 hours. So we'll see how it goes. I get a sort of take Lucas's direction as a giving me freedom to be completely chaotic and go back and forth. So hopefully I'll jump to some of the proof ideas towards the end. So the plan is to I'll talk about the work on regularity of essentially Codimension 1 regularity theory for minimal surfaces, and also more sort of related CMC surfaces, and in fact you can go even beyond that. But what I want to focus on is the CMC case. So the history of this is that somehow the point at which I want to start is the work of Schoen-Simon-Yau and Schoen-Simon in the mid-70s and early 80s, where they proved a priori estimates for stable minimal hypersurfaces in Riemannian manifolds. And then sort of more recently, turns out that you can actually push this theory quite far. Using these a priori estimates, you can get rid of the assumptions on the singular sets and so on. And so I did some work on the minimal case, as some of you know, stable minimal hypersurfaces. And then with Costante, we were able to extend that to CMC case, and there's quite a big difference between the two cases. So that for that reason, I'll just jump to the minimal CMC case more or less straight away, and along the way highlight the differences between the minimal and CMC case under the assumptions that I want to present the theory. And then once you have the CMC case, it is actually, it does look like going to even further. The case of mean curvature prescribed by an ambient function with sufficient regularity, it seems like a fairly, there are some subtleties, but main GMT ideas seem to be already on the CMC case. So that's the CMC case is sort of the hardest. Right, so we're going to start by giving a title. And what I want to do is I want to divide up the talk into sort of a brief discussion about classical theory, which is assuming C2 when the mean curvature makes sense everywhere, and when the hypersurfaces are oriented. So we can talk about enclosed volume and so on. We can present the condition of being CMC as a variational problem, and then we will go to I'll discuss the a priori estimates for the embedded CMC guys. This is the work of Schoen-Simon-Yau and Schoen-Simon under so-called strong stability, and then discuss how to use those as estimates to get to the varifold case. Okay, and from the outset, so we're going to keep the variational assumptions actually that are sort of classical. We try to keep that the same in the varifold case as well. Okay, that's the main point of the one key point of the extension. We were not going to assume anything across the singular set will only restrict to the regular set when imposing the variational assumptions. Okay, and then we assume some mild conditions on the singular set, and then control the singular set completely to the sharp results. Okay, that's kind of the summary of what I want to describe. So the classical setting. So we're going to assume that we'll work in the Euclidean space, some open set in the Euclidean space. Now everything generalizes to Riemannian case, as is usual with regularity theory. That is not difficult to do. It's only technical modifications you need, and I won't go there. I just will work under the Euclidean setting, and then in the classical setting we're going to assume that M, so n-dimensional submanifold in U. So we're going to assume that this is embedded for now, oriented C2 with locally finite measure. Right? So we're going to assume that n-dimensional measure in compact subsets is finite. Okay, so we'll fix an orientation. So fix continuous unique normal. New. And then once you fix that, we can define a functional. So we let so fix also a number lambda. And then let j sub lambda be script a of M plus lambda times wall, shorthand for enclosed volume of M. So script A is the n-dimensional Hausdorff measure, so that's the area. And this here is the enclosed volume. So this actually you can write down this formula I'm going to write down is not so important for most of the talk, but I'll since you're in Euclidean space you can do this, so may as well write it down. This is so the coordinate vector field. This is x dot nu x and integrate on M with respect to the Hausdorff measure, like that. And by the divergence theorem, so if you did in fact have, see, there's nothing here in defining this about, you need orientability, right? Because I've chosen you need normal here, right? But other than that, you don't need anything else, M to be compact or enclosing a region. But if it does, then this is indeed by the divergence theorem, this is the enclosed volume, right? So this is if M is the boundary of some compact region like this, and this is divergence theorem. Divergence of the coordinate field is n plus 1, so n plus 1 times the volume is given by this boundary entry. Nu is the outward normal. Okay, so it's an oriented volume. If you switch it nu, so nu is fixed and this is how it's defined, but if you switch the direction, it changes the sign. Okay, so we have this functional, and then we can compute the first variation of this. So we consider deformations as is usual. So C2 deformations. And starting with the identity, and also phi t of x equal to x for every t and x, every t and every x outside a compact set. So this is okay. So you can take this family of phi t's to deform M, and then with respect to that deformation, you can compute the first derivative of j lambda. So if I let mt be phi t of m intersect k, so everything is happening in, so that has finite volume, right, by assumption, and we're only deforming this compact piece, and then we can compute this area, and this is well known. This is first variation formula, where x is initial velocity, and then this is related to the mean curvature by this formula. And then ddt similarly of the enclosed volume is given by an integral of x. This is x dot nu, some x here. So therefore we got the ddt of j lambda mt at t equals 0 is given by this formula, which is x dot lambda nu minus hm, like that. And so that shows that so if this is 0 for every such deformations, then this says that the mean curvature is lambda nu, so it's CMC, right? So this characterizes. So two consequences of this. First, so this implies that first of all, M is CMC with mean curvature equal to lambda nu if and only if M is stationary for J. And also we also get this from this first conclusion, in fact, that M is CMC. Now I'm not specifying what the mean curvature is. This condition is equivalent to saying that M is stationary for the area function, or like with respect to area for volume preserving deformations. Okay, so these are fairly easy and standard calculations. And now let's just talk a bit about second variation. So the first variation's condition is stationarity with respect to volume preserving deformations. The deformations that fix volume is the same as saying is CMC. Now when it comes to second variation, there is a difference actually. There's hence the two notions of weak stability and strong stability. Okay, so stability. So we make a definition now. So we'll assume M is CMC now. M is weakly stable if M is stable with respect to area, i.e. second derivative is non-negative for volume preserving deformations. Okay, so the class of deformations just characterize as CMC condition. If you stay in that class, if the second, so then of course area function is the same as J, right? Because you're preserving the volume, that's constant. And if it is stable with respect to the area functional, then we'd say it's weakly stable. Okay, and it turns out that it's a calculation one can do. This from this you get an inequality. So this is equivalent, in fact, to the statement that integral of a squared zeta squared, so this is the second fundamental form, a, is less or equal to integral grad zeta squared. This holds for every zeta smooth function with compact support on M, and with the condition that, so this has to be volume preserving, which turns out to be the condition that average of zeta on M is 0. Okay, so this is the weak stability condition. And then if we drop this assumption and assume that's always true, then we say it's strongly stable. If this inequality holds for any. So the strong stability is a notion that's certainly the natural notion for minimal case, when there's no lambda equals 0. By the way, everything I'm going to discuss from big start to end, this lecture applies directly by setting that lambda equals 0 to the minimal case. You don't have to make a distinction. There's nothing. It becomes a strictly special. The minimal surface theory becomes a strictly a special case. So in that case, strong stability is the only kind of stability that's relevant. But for CMC, when lambda is non-zero, this is the more natural class of stability, notion of stability. So okay, so this is stability, and now let me discuss a bit about a priori estimates. So once you assume this stability and stationarity, then this is now the work of Schoen-Simon-Yau. So this is so I said, so back here I said M is embedded, right? But there's no properness assumption here. Only assumption is that it has finite volume in compact sets. In other words, I can allow a singular set. So let me do that now. So in above, there is no assumption that the singular set, this is now a definition, which is the topological boundary of M inside of U, that we are not assuming that this is empty. Okay, so in principle we can let that be a non-empty set, the singular set. So you should keep the picture in mind. Is this, if you're in a wall, let's say, so you could have an embedded guy, and then here, so that's the point in the singular set, right? It's in the closure, but not. I'm going to use the letter M to denote the embedded part of M closure. In other words, we are not going to do anything stupid like removing a point from nice smooth M and calling it a singular point. So if M closure is embedded, we are going to include that point and redefine M. In other words, we're going to remove all the removable singularities are already removed. Okay, let's just agree on that. Subject to that, this is the singular set. So what? So Schoen-Simon-Yau estimates say that so these apply to low-dimensional hypersurfaces, n is less or equal to phi, and singular set is empty. And then M is stationary and strongly stable. With J lambda. And then we'll assume a mass bound like that. So I'll write down the estimate in a ball. So let's assume U is, I'll use B for the unit ball in Rn plus 1. So we work in here. So this is the mass in a ball. And then the estimate says that under these assumptions, so we'll also assume 0 is in M, so M is not somewhere near the boundary of this ball or somehow, some little bit, it just stays somehow in the middle. And then under these assumptions, the curvature at the origin or curvature in the interior is bounded. There's a fixed bound. So the supremum in B1 half, this is bounded by some constant which depends only on little lambda, which is the mean curvature value, and mass bound. So this was proved entirely by PDE methods, just working out the Laplacian of the second fundamental form and using, first proving integral estimates for higher powers of A, and then using that to essentially use the Morse iteration process to get a sup estimate out of the equation. So this is a PDE based proof entirely. And then few years later, Schoen and Simon, by completely different methods, GMT methods, generalize this in two ways. There's a statement for arbitrary n now. We need an extra assumption to make that true for arbitrary n, and also they allow a non-empty singular set, right? So this is the point. They allow a certain singular set with a certain assumption on the size of the singular set, and then they were able to carry out similar prove similar estimates, curvature estimates. Now it is extremely useful to allow a singular set because even if you're studying smooth objects, you might want to take limits of these things under area bounds and mean curvature bounds, and in the limit you expect to get singularities. The singularities are unavoidable. So proving estimates allowing some singular set is actually extremely important thing to do. So so this is as M as above. Now we're in arbitrary n and M as above theorem. So it's strongly stable. They're both strongly stable. Okay. I mean they had in mind the minimal surface case really. So that's the natural assumption is strong stability. In fact. But out of their work, so what I'm writing down is sort of what you get by easy modifications of what they did, right, to suit the CMC case. They were firmly looking into the minimal case in proving this. So M as in above in this theorem, and then accept we're going to assume that this singular set here, so the dimension, Hausdorff dimension of the singular set at most n minus 7. Okay, and then okay, so that's fine. Then if you're in dimension 7 or higher, we need another assumption. Then this is we want the height of the surface relative to some plane. Let's just take it to be Rn. This is the n plus first coordinate. This is small, plus the mean curvature is small, so I put mod lambda here. Well, this only depends on n and big lambda. So that's an assumption. Okay, this is like a small excess assumption. I'll put a square here because to match with that. So then they prove curvature estimate essentially. I'll write it as a sheeting theorem. What they proved is that under these assumptions, you get, so maybe I didn't say it in the optimal way. So in this case, when you have flatness, this is assuming close to in L2 sense close to a plane, they prove that it's smoothly close in the interior, and in this if lower dimensions up to 6, you don't need this assumption. You get a sup bound on A, mod A, like in Schoen-Simon-Yau. So for n, so conclusions. So this is again, C depends only on lambda and little lambda. And then for arbitrary n, for large n, then under those assumptions we get a sheeting. So M intersect B1 half the cylinder. It's convenient to write this in the cylinder now. This is M closure now, right? Because I'm allowing a singular set, but the conclusion says that the singular set is not so bad. This is the union of graphs where UJs are C2 and in fact smooth. They're ordered. And they're allowed to touch, right? So the only kind of singularities that's going on here is just smooth sheets touching. So if only two at a time by the maximum principle. So if a point is in the singular set, then two of these agree. Uj of x equals uj plus 1 x for a unique j. Okay, so the picture is that, which wouldn't happen if lambda is 0, of course, by the maximum principle, but it can, in general, it can happen. That's touching. And the picture in the half ball is like this. There may be a sheet touching this here. So that is a singular point by strictly speaking, by our definition, non-embedded point, but it is really just two smooth sheets touching. and there can only be two, right? This says that there can't be a third sheet touching this because you have C2 regularity. That's enough to say that by the Hopf boundary point lemma, this really only two things can touch. You need the C2 regularity for that. Otherwise, that can go wrong. Right. So this is the work up to early 80s, and now we're going to jump ahead. Let's see. I think I should give a break at some point, right? Some point. Let's see. We started at 1. We'll go for another, I don't know, like 10, 15 minutes maybe. Yeah. Maybe I'll keep that functional there. Right, good. Yeah, I was going to make a remark about that, yes. You are quite right. I'm not doing full justice to the Schoen-Simon work, although, so here's the remark. In their proof, they allow, in fact, a weaker condition, in fact, than n-7. So this assumption here, this, you don't need, it doesn't need to be that strong. So in the proof, they allow, in place of 1, that the n-2 dimensional measure of the singular set finite. And in the conclusion, conclude that there is a regularity part, in other words, right? Assuming this, they conclude that, in fact, the dimension of the singular set is at most n-7. Now, the reason I stated it that way, at least from the point of view of regularity theory, in terms of extending all this to a varifold setting, all you need is that. Okay, the theory to work under this assumption, and that's one reason. And the other reason is that the proof is the same. Actually, all the difficulties are already in that case. So, but the difficulties the proof are all in case 1, and for the generalization of the theory to varifold setting, this is coming up next. All we need is 1. So this generalization depends on the Schoen-Simon estimate in an extremely crucial way, but only subject to that assumption. Now the reason, so I like to state this theorem in this way because there is a very nice analogy that you can see with PDE if you view it in that way, because what it is saying in the end, so I'll present the new sort of theory in a minute. But what's going to say is that, and as I said, the new theory uses these estimates, and it says that if you, so the philosophical is saying that if you can prove a priori estimates assuming the expected the control on the singular set, which is n-7 dimensional, then you can remove that assumption. Okay. And from PDE, this is nothing new, right? We know that You want to prove, smoothness of solutions via a priori estimates. We know how to do that, right? We approximate. So the difference is that in PDE setting, often that involves an approximation of the solution entirely by smoothing out coefficients or whatever, by smooth solutions to a related family, and using a priori estimates for smooth things to pass to the limit, right? To show that so sharp regularity conclusions follow. Here, of course, the story is much more complicated. There's no, given an arbitrarily singular varifold with some kind of variational assumptions on the regular set, it's not clear how you can, there's no approximation of that by varifolds with small singular sets. The proof is not that straightforward. However, the philosophy, there is a certain approximation, there's a certain linearization process that goes on in the proof, which is a way of approximating these varifolds when they are flat by graphs of harmonic functions, and within that approximation, Schoen-Simon estimates play a central role, proving regularity for the linear problem, linearized varifolds. That's where the estimates are one of the key places in the general theory that the Schoen-Simon estimates are used. In once you know enough control on the singular set, this much control. Okay. So when you state it this way, the analogy becomes quite clear with PDE. It is a good sort of thing I like to do often when this analogy of the PDE setting in these various results.
Sorry, the CMC case, can you do it with n-2? It wasn't clear to me.
Sorry?
Can you do it with n-2 finite, or do you really need n-7?
You only need to know Schoen-Simon theorem, assuming a singular set has dimension n-7. So you don't need to know that the Schoen-Simon theory is true under this assumption to get to the varifold theory.
So in the non-varifold case, you showed that if you have that assumption, then you have this assumption, which meant that actually the n-2 measure was actually 0, because measures.
That's right. That's right. Schoen-Simon assumed this, and they actually show that in fact that implies this. Right. But what I'm saying is that first of all, their proof, all the difficulties in the proof are already there even under the stronger assumption. See, I'll show you why that is the case. See, the only way they use this assumption, so this is used so psi is used in the Schoen-Simon theory to get the following implication, that the stability inequality, so which is assumed on the embedded part, right? We only deform by test functions which are normal and supported on the sort of vector fields that are normal to the embedded part. So the stability to begin with, the assumption is that on M you have this inequality. So M here is the smooth, is the embedded part, right? And then, but if you know that, so that's the assumption, and then if you know that this and singular set has n-2 dimensional measure finite, it's an easy argument to see that this implies, in fact, the stability in the stability inequality you can take test functions which are compactly supported in the ball. So these test functions are only required to be 0 in the boundary of the ball. They're allowed to behave arbitrarily over the singular set. Okay. So in particular, this implies the second fundamental form is in L2, locally L2, right? So in any compact subset of the ambient space, this is finite. Okay, and for that, this is, you can't do any better than that. This is a capacity argument. depends on the quadratic nature of this inequality. And this is, you can weaken it a little bit to say that 2 capacity is 0, but that is the absolute. So to getting this a priori, making this conclusion,
So the point
you
is
can.
that this is a capacity argument.
It is, yeah.
A capacity removable singularity.
Exactly. It says that 2 capacity 0 sets for this kind of inequality are removable, right? And that's an easy test function argument. That's easy. It's well-known fact. And that's the first thing they do in their paper. And the reason, so then once you have this, they are very free to choose test functions that are very standard test functions in the ambient. Right? The problem with this inequality, getting information out of this, is that you don't know where the singular set is. So because this insists that your test function be supported on the regular set, you can't construct good test functions without really knowing where the singular set is, right? And this implication shows that you don't have to worry about that. Yeah.
And these comments you made about approximating locally by grams of harmonic things
Yeah.
and getting a priori estimate, this is pretty much all proofs in geometric regularity and geometric measure theory come sort of.
Yep.
Right?
Yeah, that's right. This is an idea that goes back to Di Giorgi in the area minimizing hypersurface case. In fact, there's versions of that. Of course, more sophisticated increasingly,
Right,
depending on the
more sophisticated.
right. And
Sort of
but the gist,
oversophisticated.
yeah, exactly, right. Linear.
Because in some things, if you want to do a primitive asymptotic expansion of the area functional, you get the harmonic functional, square of the Laplacian plus lower order expansion terms.
Yeah, that's right. That's where it's coming from. So while we're at it, since I'm discussing this singular set assumption, let me also point out this will, in fact, be a corollary of the theory I want to present next. So as I said that a priori, this is if you want to make conclusion like that a priori, you can't really do too much better than that. But however, now let's think about what could happen if I allow a larger singular set. So so now I'm jumping all over the place, taking full freedom. This is so suppose you do allow if you allow this and no further assumptions, then the conclusions fail. Because you could easily have two parts of spheres intersecting like that. These are stable, CMC, and they can be made flat and all that, and this singularities are there. But more threatening. So this is sort of okay. You have now allow immerse, you might say, right? They're so bad. They're just the singular because technically they are. But however, more threatening is that the limit points of such things, they can become non-C2. You can get branch point singularities. And also get branch point singularities. On a set of positive. So branch points are usually, it's a codimension 2 phenomenon. So you get either you get a whole set of positive n-2 measure or none. So if one happens, then they happen. This is kind of heuristics, and it's, in fact in some cases this can be shown on a set of positive h n-2 measure. So what do they look like? Well, so one nice picture you can imagine for this is this sort of example. So this is you should, if you don't understand this picture, which I don't, think of this as a real part of z to the 3/2 on the complex plane, right? So this is
That's like an attempt to draw the branch curve. Oh, it is. Okay.
right.
That's what I thought. Okay.
So this is like so surface that looks like this. So this is, I'll say like because this is not a minimal or CMC example, but this is a sort of like a linear analog harmonic example. See, you lose C2 regularity, right? This is C1 1/2. The origin. That's the threatening thing. You don't get C2. Now, of course, you can construct. Somebody should check this, but minimal surfaces you can construct that are asymptotic to this guy. So they can be constructed. In other words, the first term in the expansion is this. But it shouldn't be too much of a stretch from there to some CMC example where that's
possible branch point. Do you also get a branch line like in?
Yeah, you get these immersed curves. So these are meant to be. This is in 2D, so this is a point. So it's positive n minus 2. But in general, of course, you can then now cross this with
Right. Okay.
Rn minus 2 to get a branch line. But more generally, in the minimal case, there's examples of these. They can be constructed. I wrote a paper with Leon Simon about this, and then Brian Cromwell generalized that, and I think he has the state of the art on that construction of branched stable minimal hypersurfaces. They do exist. But CMC ones should also exist. Shouldn't be. See, the point is that when you linearize this at that point, by rescaling here and then also dividing by the height, L2 height, you literally get, if you had a minimal guy, you get this guy, right? Also, if you see CMC guy, you get that guy. So if you had C2 estimates, the limit guy should be C1 alpha for any alpha less than 1, right? So but this isn't. This is only C1 1/2, right? That's the reason why you're not going to get C2. So C2 regularity fails in this. That's the more threat if you allow this. Okay, but so then the next natural question to ask is, what about this? Okay, and this is okay. So the whole theory goes through under this assumption by a completely different method, right? Which relies on Schoen-Simon estimate, but it's not a priori showing this implication. Okay, this is in fact a corollary of the next theorems. Right. So time seems to be flying. Maybe this is a good time. To have a. So I'm gonna move on to varifold setting and discuss the new theory, and then as much as I can about the proofs of differences in the proofs and so on. Okay, short break. Okay, so I just checked my notes and I've gotten through 4 pages out of 11. Right, so now we're going to move to varifold setting. So we're going to start with the varifold. So B and N varifold in B, i.e. a non-negative Radon measure on a B cross the Grassmannian Gn So we need a topology on that. We just take the product metric. And then, so that's just what a varifold is. I just gave you the definition. And then we say V is integral. So we write V, so I'll use the notation script IVN for the set of integral varifolds on V. If there is a rectifiable, a countably and rectifiable set M in V, and a multiplicity, a function theta, which is called the multiplicity function, which is defined on M and takes positive integer values. This is locally H and integrable. Okay. So in particular, because theta is bigger than or equal to 1, this implies that this set, this countable and rectifiable set, is locally finite mass. Right. Okay, so this is the setting we're going to be. This is a nice general class of objects which are suited for geometric purposes. This is a nice generalization of. It turns out that because of the various sort of compactness theorems that were proven by Almgren and Allard and so on, these integer valued, these integral varifolds turn out to be the sort of the right class to work in, right, when passing to limits of smooth objects or proving existence theorems and so on. Okay, so this is our starting point. We're going to start with something in that class, integral and varifold, and associated with this is the weight measure, which is a Radan measure downstairs on B, defined by just ignoring the Gauss-Mann variables. So V of Gn, and I guess I didn't quite finish what I wanted to say. So this I didn't. Okay, so this sentence I should finish it. I'm starting with the varifold here. That's the right way to think about varifolds on the measures on the Gauss-Mann, because then you can pass through the limits and things like first radiation. Okay, that's the point of doing it that rather than downstairs. But integrality means really that associated to this you have this pair such that V is given by, so V of I'll write down the action of V by duality on continuous functions with compact support. So V of phi is simply integral of that and theta x Hn. Okay, so if this is true, so this is true for every. Take any continuous functions in compact support in this set on which you have the original measure V, and that's the action, and that's defined by, in terms of this rectifiable set, in this way. Because M is rectifiable, this makes sense almost everywhere, right? There's a tangent space almost everywhere on M. Okay. So we're going to assume this always holds for our varifolds. And now associated with this is the weight measure, which is this, and this is by this formula, this is the same as integrating theta on M intersect A. And what we're going to do is, so then once you have a varifold like this, you can define first radiation of that relative to the mass functional, this functional here. V of B by taking the same kind of deformations. We have the set now, right? We have this rectifiable set. We can deform that by the diffeomorphisms that we considered before, phi t, get a deformation of these varifolds, and then compute the first variation of mass, and we get very similar expression for the first variation. So Vt, so let's say V is our guy, m and theta, and then define Vt, which is a deformed guy, phi t of m, and theta composed with phi t inverse. That makes sense. This still has locally finite mass because phi t is a proper map, right? It's a diffeomorphism, so that's you stay in the same class. And now we can compute the weight measure, the total weight measure in the compact set, where K is the compact set in which this phi t is doing anything, right? And this gives us the formula dV. So that's theta dHn. And this again makes sense because this to compute this, we only need to compute this almost everywhere because it's an integral. And there's a tangent plane almost everywhere. So use the same formula as in the smooth case. Right? This divergence is by projecting onto the tangent spaces. Okay. So that's the first variation. And now we say, so now we have to distinguish a class for which mean curvature makes sense. Right? There's no smoothness assumption at all. This is a very, very singular setting at the moment. So we say an integral varifold has generalized mean curvature HV. So this is a vector guy, vector valued function. If HV is locally L1 with respect to this weight measure, and it satisfies, so we're going to do this by analogy with the smooth case, right? So we insist that this formula holds. Okay. So that distinguishes a class. Well, still, it allows a lot of singularities. In fact, so let me just define the singular and regular sets of such a thing. Which board should I just make? What we care about is that under first assumptions on the first variation on this particular mean curvature. So by definition, it's in L1, but that's such a weak assumption. It doesn't give you any regularity at all, turns out. But assuming more about HV, you can hope to say more about the regular set of this varifold. So reg V, this is a smoothly embedded part. Well, let's say C2, embedded part. Of the support, which will be smooth because we're going to assume this is going to come with some variational assumptions which are natural, and then in the case of CMC and so on, with this, once you know C2, everything else follows. And the singular set is the complement. So everything is interior, right? So we're going to stay inside the open ball here. Sing V is the complement. And I want to define another temporarily different larger regular set, reg 1V. This is the C1 embedded. Okay. So at the moment, with just H in L1, this support could be the whole space. Of course, when I say C2 embedded in L1, it's n-dimensional, right? This is what we care about. We want this to be hypersurfaces, so n-dimensional. So it's not hard to see that you can, under these assumptions where the mean curvature exists, and in fact in LP for P less than n, where n is the dimension of the n plus 1 is the dimension of the ambient, you can, by putting little spheres around rational points, you can construct examples where the support is the whole space, right? So and it satisfies still this mean curvature assumption. So we need something more of a handle on the mean curvature to say anything about whether even a regular set is non-empty. So that's Allard's theory. So this is 72, this landmark paper. Allard says that if HV is in LP locally with respect to the weight measure for some P larger than n, then the regular set is non-empty. In fact, it's dense. So of course, open by definition, it's now dense. Sorry, reg 1, I meant reg 1, not reg V. You don't know reg 1. So here, in fact, so that's C1 embedded part. And in fact, reg 1V is of class C1 alpha, where alpha is 1 minus n over P if P is finite, and any alpha between 0 and 1 if P is infinity. So if the mean curvature is locally bounded, you don't quite get C11, but you get arbitrarily large alpha less than 1. Now this is again PD analogy of this is the Cauldron-Sigmund theory, right? You're sort of doing something like this: Laplace U equals F weakly. F is in LP implies U is in C1, 1 minus n over P. Okay. So it's W2P in fact, and then which embeds in there by Sobolev embedding. So that's Allard theory is really this. This is a trace of the second fundamental form. Here's the mean curvature. Yeah, so this is the trace. Yeah, this is the trace of the Hessian. And here we're saying the trace of the second fundamental form is in LP. The only difference is that here you get everywhere, right? This is true, but this is only a dense set. That's the nonlinearity effect of the problem. So we get something, but there's not much, right? This is a deep theory. This is a lot of hard work went into proving this, and there's an estimate we'll write down in a second. But you do get this non-empty set. But in measure, you had to keep in mind that in measure this says nothing. You could have a fat Cantor set of arbitrarily large measure, nearly the full measure of singularities, nowhere dense set. So in measure, this could be extremely small, and in fact, there is an example due to Bracke that precisely demonstrates that. There is a construction that gives you a singular set of positive two-dimensional measure. This is a 2 varifold in R3, which has locally bounded mean curvature. So even when P is infinity, your singular set could be large under these assumptions. So example of Brachy shows that Sim V could have positive n-dimensional measure. Even if P is infinity. So, but because we have a regular set on the other hand, now we can start to make hypotheses on the regular set, right? And which is what we're going to do next.
So for the stationary case, you expect better, right? Maybe n minus 1 dimension.
Maybe you do. I mean, yes, I don't know how. Well, right. I mean, who knows? Yes, you would hope that at least. So here's the problem. I mean, let me illustrate this. In fact, so the Brachy example actually sort of somewhat simplified version is the sort of this picture here. You take two sheets like this and then you connect them by catenoidal sort of necks, a sequence of necks approaching that. So it's a singular point. It's one point, but in this picture at the moment, just one singularity. But these are the most threatening singularities. This type of singularities are the hardest to control because the level of tangent counts. This is flat. And what Brachy example does is that it constructs this example such that by piecing together pieces like this, a set a positive measure of that here. Now, of course, it's not minimal. And nobody knows if even with one singularity there's a minimal example of this. So it's an open question. So it really comes down to understanding this isolated singular question, this well-known open question in classical sort of minimal surface theory, whether there's an embedded minimal surface and isolated singularity in R3. And resolving that, I think if that is the answer is no, this can be ruled out, then yes, then you would expect that singular set is maybe.
Details of this example are in his book.
Details of this example, yes. Right, some, yes, very sort of short amount of details. But it's also explained in Klaus Ecker's book on mean curvature flow. Yeah, so that's the thing. So it really comes down to try to sort of understand. Now you think about this and then, okay, so that's, when you look at it this way, it's sort of, you feel like, okay, that probably doesn't exist. But then this is why I keep kind of going back and forth. You look at that branched example that I drew, right? Take a minimal guy like that, and then these curves you might conceivably desingularize, right? In some way. So this local infinite topology could potentially happen in an example like this, where you desingularize a smooth crossing. Of course, the question is whether you can do all the way to here. That's the difficulty. But right. I mean, I wouldn't commit either way actually to that. But yes, you would hope that this can be ruled out. Otherwise, really, there's very little hope of developing a regularity theory for just for stationary varifolds. That's a major open question in GMT. Right. Right, but we are going to assume stability, and then on the regular set, and then that, somewhat surprising, that says everything basically, right? with a few other mild assumptions. So let me just quickly, as I promised, write down Allard's estimate that led to this conclusion here. So there's a similar to this Schoen-Simon cheating result I mentioned. There is a theorem of Allard which applies to multiplicity 1 variables essentially. So they assume HV is in LP log. And then assume that the mass ratio is less than 2, bounded away from 2, okay, for some delta, right? And then assume that this variable is flat, exactly as in Schoen-Simon assumption, but now we have mean curvature not a constant but some LP function. So we take the LP norm of that. So we're going to assume that the height term, this is true in arbitrary codimension, but I'm just writing down codimension 1 version. So this is the excess here, and then we have the LP, so the mean curvature. We're going to square everything, so it's 2 over p. This is less than epsilon, where this epsilon depends on delta and the mass bound. Delta is the mass bound here, and then p and I guess. So under these assumptions, Allard's conclusion is that the interior support of V intersect B, some interior ball, fixed size, call it beta. Of course, assume also the origin is in the support. And then this is a graph. Uj, and Uj is a C1 alpha function, and B1 half, where alpha is 1 minus n over p for finite p. Okay, so this is the Allard cheating theorem, if you like, and this is the assumption on the x-axis. So what we're going to do next is take such a variable and require additional assumptions based on what we have already seen. Some counterexamples I've shown and so on, motivated by this kind of thing. I'll motivate each of these hypotheses that's coming up. So we like to build a theory. Yeah. Pardon? Yes. So I would like a sharp codimension 1 theory. Varifold theory for CMC. Okay, this is what we're going to do next. So the first assumption is that we have V integral in varifold on P with HV in LP. Okay, and then Allard regularity gives me a reg 1V, the C1 regular part, which is in fact C1 alpha, And then, so we are looking for a CMC theory, but then if you look at that functional J, so J lambda, which is area plus lambda times volume, enclosed volume, this only makes sense if you have an orientation, right? So you can't really make sense of this functional on the whole varifold. But you have the regular part, C1 embedded part, and you can consider orientable pieces of that. And on those pieces, all they are at the moment in measure, you can insist that those pieces are stationary relative to this function. Okay, that's the first variation assumption we're going to make. So this requires infinity. So we're going to assume our second assumption. So this is 2. Any orientable portion of reg 1b is critical relative to J lambda. For some chosen orientation.
Quick reality check, but if you take this approach, then the functional vol doesn't really have the elementary geometric meaning you introduced before, right? There's no enclosed volume if you take a tiny piece of your object.
Well, even before we didn't, right? Even in the remember there's a formula that defines.
Yeah.
So I took it to be the definition.
A formula, but there's no enclosed volume in some sense, right?
Well,
it makes sense.
It is the volume in the cone, actually, if you think about it, right? If you take the embedded part and if you look at the cone, right? This expression gives you the volume of the. So when when it's not closing up, right?
Okay, I see.
Right. If you really want that, but yeah. So right, yeah. Okay. Right. So this is stationary. So this is our first variation assumption. So maybe I'll box everything, all the assumptions. It's going to be a couple here. So this is the first. So then, so what we're looking for is really when I say codimension one varifold theory, we really need it to come with compactness statement, right? So the important thing is that codimension one, let's say a compactness result compactness theory should go there actually with good regularity conclusions. This is what we're after, right? And we know from the experience of standard of the Schoen-Simon theories tells you that you take limits of smooth guys, they can develop singularities in the limit. Codimension 7 singularities. So we like to make those same assumptions, same conclusions, right? When I say good regularity, I want the singular set to be codimension 7. Now you have a bit of a dilemma now, because in the minimal case this is all fine, right? This is in fact, so I did some work on the minimal case first, and that all generalizes in a nice way. But in the CMC case, embedded things are not going to be embedded in the limit because of the lack of the two-sided maximum principle, right? So lack of two-sided maximum principle means embeddedness is not the right. We have to give up on embeddedness. To get compactness, to have a compact class. in the CMC setting. Right, so simple examples like 2 cylinders, so you can have, this might be your sequence where these are separated by 1 over j, 2 cylinders, and in the limit, so this is in fact the worst case actually, they do overlap, not on a small set, but on a set of positive n minus 1 measure, right, which is bad for stability, right. We from before, we know that something like Schoen-Simon assumption is natural from the point of view of stability inequality. But here if you're allowing this kind of touching singularities, they can have large measure, they can have positive and minus 1 measure. So compactness demands you have to let that happen, right? You don't want to make an assumption like Schoen-Simon, which says that the singular set is n minus 2 measure finite, or even n minus 1 measure 0. That's still bad. You're not going to get compactness. And on the other hand, stability has to be modified to what you mean by. So you have to assume stability as an immersion here, allowing these sheets to move separately, right? So this is second assumption is stability. We're going to assume not only on the embedded part, but on this generalized regular set, which is still C2 but now immersed. Okay, so that's the stability assumption. So everything is still classical, namely the second fundamental form, stability inequality. All of those things are exactly as before, but now for immersed part, right? Which makes sense, right? CMC theory for stable theory, it works for CMC immersions. The exact same inequalities I wrote down. So this is the third assumption. C2 immersed part, which is non-empty because we know that as soon as we have the first variation assumption here, reg 1v, if it is stationary for j lambda, then by PDE this reg 1v is already reg v, right? It's smooth. So certainly there's a C2 embedded part, and more generally you might have touching singularities. You're going to allow that, right? That's what I mean by this. Let's call this gen reg v is weakly stable for the functional j lambda. So i.e. so on test functions that are supported on that set, generalized regular set, we assume this inequality. So, yeah. This is as an immersion, okay? Stability. This is stable as an immersion. The whole C2 embedded immersed part is, in fact, this piece is actually this corresponding to that is because it's CMC. See, I'm assuming C2, right? That means the mean curvature is continuous up across that touching set, right? So it makes sense. So you can actually define it as an immersion of an abstract manifold, and on that we're going to assume stability by moving sheets independently. Right, so that's 3. And then, so those are the variational assumptions. Now we're going to need, so here still you can have branch points, right? So if I allowed this sort of crossing, which so far I haven't ruled out, right? Then again I can't get C2 conclusions because of that branched example that I drew. Yeah, these crossings could limit on a branch point, and I don't want that. I said I want a codimension 7 conclusion for this, for the genuine singular set, not a codimension 2 branch set. I mean, well, okay, you might ask what happens under these assumptions. That's a really serious question here, actually. Understanding branch points that can happen under these assumptions, but for the moment we're going to find a way to rule that out. And this is assumption 4. So rule out with a view to ruling out. It's not clear that this next assumption I'm going to write down is going to do that, but it is in the proof, right? That it comes at a lot of hard work. So with a view to ruling out branch points, assume. See, in this example that I drew, branch points are limit points of immersed guys, right? So you expect that sort of to be true in complete generality, and in fact that is the case. That is shown by the theory, in fact, right, by the conclusions. But the assumption is that we're going to rule out these classical singularities. V has no classical singularity. What is a classical singularity? Well, I'll just draw a picture here to show you what a classical singularity is. This is meant to be a sort of a 3D picture. These are C1 alpha sheets coming together in a nice regular way all the way to this free boundary here, common boundary. So point P here is a classical singularity. So C1 alpha hypersurfaces with boundary meeting at a common free boundary. C1 alpha, yeah, embedded. So we take a tangent cone, then it looks like, in this case, like 3 half planes. And we're going to insist that at least one pair is transverse. Okay, there could be some finite number of sheets like this, but some of them might come in tangentially, but at least one pair is transverse. So if you take a tangent cone, you see an angle, right? At least one angle, positive. So we're going to rule out this structure. This is going to be a structural assumption now, right? In checking this assumption, you're allowed to assume C1 alpha regularity, okay, in this way. Nothing mysterious. So it's a checkable assumption. And then, so far what can happen? In the minimal case, actually, that's the sort of the end of the story, in fact. But in the CMC case, there's a serious difficulty that comes about because of the following example. So you can have this guy. This is a circle, or a cylinder, if you like, half a cylinder. And then there's another one which is doing this. It overlaps with that on that side, but then suddenly decides to go this way. So this is CMC, and everything, it satisfies all these assumptions I've said so far. It has no classical singularities. This singularity here is a tangent cone is a plane, right? No angle. And this is CMC1, mean curvature. You know, if you take radius 1 here, so it's a CMC. And the embedded part is certainly classically CMC. But what fails is C2 regularity. So here there's no C2 conclusion here. This is C11. This sheet is C11. This is C2, but this is only C11. Right? So C2 regularity. So the conclusion I'm aiming for is that there is a codimension 7 singular set, and everywhere else it is C2, possibly touching two things, but C2. And hence C infinity. Okay, this is what we want to do. So it's a classical CMC immersion away from a codimensional 7 set. This is what I'm going for. And we know we have to allow touching to get a compact class. Okay, but the obstacle is this. So far, we've got to deal with that. Right? And the assumption that's necessary for this again, is really literally ruling out that kind of picture. In other words, you're allowed to assume C1 alpha regularity in checking this next assumption. So we can make a definition now. P, a singular point, is a touching singularity. If there exists sigma such that the support of V intersect V sigma P, is that mere more. This is the union of two C1 alpha embedded hypersurfaces for some alpha so if I want to rule out, I've dealt with classical singularity, so let's assume P is not a classical singularity and it is a singular point, so this is not in reg 1v. That means that, so P is certainly obviously in here and therefore it's in the union. It must be in both, right? Otherwise it would be reg 1v. It's not in. So therefore the picture here is that this bit looks like that, and of course away from that in this ball, as far as the definition is concerned, you are allowing sheets to cross. That can happen away from here or have another sort of touching point here. We don't know, right? It could be large. In fact, in this example, so there's really only touching singularity, one singularity, but sheets do overlap on a large set, right? That's in this bit is in reg 1v or reg v in that case. So that's our definition, and then what we're going to do is that with the view to knocking this out, we're going to assume that the coincidence set near P, such a set, which is so we'll write sing TV for touching singularities, is the set M1 intersect M2. That's the definition. So we've got a definition of touching singularity and definition of coincidence set, which is a set where these two embedded pieces meet. And what we're going to assume is that n-dimensional measure, so the assumption, fifth assumption and the final assumption, is that the coincidence set near any touching singularity is Hn null. Okay? So we insist that the n-dimensional measure of the coincidence set, here of course positive, we would want that to happen, has to be 0 near every touching singularity. Now I should emphasize that again, that is an assumption that in which you are allowed to assume the whole structure of the varifold is 2 C1 alpha sheets. Okay? So these singularities are very mild types of singularities, touching and also classical singularities. We make assumptions on both of these special types of singularities, and then variational assumptions are also only on the regular set. The only thing that connects, goes through the potentially humongous singular set, is the one that says mean curvature is in LP. Okay? Everything else is on some regular piece. Yeah, and then so for that reason, it's sort of surprising that the conclusion of this is actually the singular set is codimension 7. So this is all we need, and theorem. This is joint with constante. If 1 through 5 hold, then there exists a closed set sigma of the support with Hausdorff dimension at most n minus 7, such that support B away from that is a C2 CMC immersion. With mean curvature equal to lambda, right? We fix a lambda there, so mean curvature vector is lambda times nu for some choice of unit normal. Okay, orientability is actually part of the conclusion here. Okay, once you know that the mean curvature is lambda, of course it's orientable, right? Lambda is non-zero. And then associated compactness theorem says that if you take a sequence, these assumptions define a compact class subject to further assumptions that the uniform mass bound, and so you're fixing the lambda. More generally, you can take a sequence of lambdas also, but provided this bounded. Okay, so that's the compactness statement here. In varifold topology, you have compactness this way. Now, once you know that compactness statement, then in a separate paper with Costante and Otis, we prove curvature estimates for weakly stable. So remember, Schoen-Simon-Yau and Schoen-Simon theories for strongly stable. But that goes through. So we prove this compactness in this paper without really proving an estimate for weakly stable ones. See, so the point is that we are assuming weakly stable, but that means that the Morse index is at most 1 with respect to J. That's easy to check. So locally, therefore, it's stable, right? These are very trivial things to check. Once you, as far as regularity theory is concerned, finite index is essentially the same as stability, right? That's a just very well-known fact and easy to check. So we can immediately, in the proof of these theorems, we can assume, because we are doing everything locally, we have strong stability inequality. That's not the hard part, right? So we can prove the compactness in particular and under weak stability without an estimate for weakly stable ones. So the point of the next result is, in fact, there is an estimate. So there's a subtle, right? Because index 1 things do not satisfy sheeting, right? As is shown by catenoid. But weakly stable ones do, right? That's what this shows, this next theorem. So Schoen-Simon-Yau and Schoen-Simon curvature estimates extend to quasi-embedded weakly stable quasi-embedded means, like I said before, C2 pieces are allowed to touch, but not cross. Okay. Quasi-embedded weakly stable with respect to J lambda hypersurfaces. So I'm not going to bother to write down precise statements, but very, very analogous. Up to dimension, low dimensions, you have pointwise superestimate on the second fundamental form. In higher dimensions, you have sheeting theorem, provided that it's small. In distance, it's close to a plane. So like I said, these are not true. Certainly not true for index 1 critical points of J lambda. But so weak stability lies in between, and the key point is that for weakly stable minimal hypersurfaces, they can only have one end at infinity. This is the theorem of Chen, Schoen, and Yau, which they show that weakly. So we capitalize on that. That's what makes the distinction. So catenoid has two ends, right? So index 1 guys can have two ends, but weakly stable minimal surfaces have only one end. And we use a blow up argument to reduce our theorem to essentially to bring it to that case. Now comes the proofs. So I had wanted to obviously discuss some proofs, but maybe we will see some proofs towards the end of this term somewhere. Right? Okay, so maybe it's a good place to stop, hoping that maybe people might have questions. Yeah.